Hello guys, hope yesterday's lesson went well for you, solving exponential equations without logarithms. Now we're going to solve exponential equations with logarithms. So obviously, the reason we're doing this, hopefully is obvious, is that the 1-1 property does not always apply. You will have equations where you do not have the same base on each side, and there's no way to make them the same, no way to cancel them out. So that is a situation, and we're going to learn how to deal with that. We will be using Desmos, which has a log button and then a log A button. I'll talk about those as we go through them. We're going to do two types of problems. One where you get an approximate answer, which means you get a decimal that's going to be rounded off. One we're going to use no calculator and get an exact answer. So that'll be different and interesting. And we're going to rewrite exponentials as logarithms, logarithms as exponentials. Actually, this is the first thing you need to know. So I'm going to skip down to the bottom of this worksheet and do this section. If you're the type who only watches a little bit and then gets to work, don't just watch this first section and think you get it, because all this other stuff is going to come toward the end of the lecture, the second half of the lecture. So let me skip all the way down to the bottom, all the way down. Here we go. Rewrite each equation in exponential form. So this is a logarithm. Rewrite each equation in logarithm form. This is an exponential. You know what? We're just going to go backwards through this. So, wow, that's a dumb one. Let's look at number 26. This is an exponential equation. 10 to the third power equals 1,000. And it's a true equation. I mean, not that you have to do this, but just to prove a point, if you take 10 and raise it, doggone it, 10 and raise it to the third power, you get 1,000. So, okay, duh, it's a true statement. A logarithm is just a different way of writing this equation. So you write this equation, log, so this is then an abbreviation of a mathematical operation called a logarithm. Just like this is a symbol for plus, I suppose math could have been done where you write the word plus or you write an abbreviation of the word plus, but no, a sign is used. Logarithm is a math operation, and log is the abbreviation for it. Now, a logarithm has a couple of parts. It has a base. The base is a small number that's written down by the letter g, and it's the same as the base in the exponential equation. So this is a base 10 logarithm, just like that is a base 10 exponent. Logarithms also have something called an argument. That's the number that goes right next to this. The argument of a logarithm is the answer to an exponential equation. The answer to a logarithmic equation is the power or the exponent from an exponential equation. So this is just a rearrangement of that. Let's look at another one. Log, the base of this exponent is a 9, so the base of the logarithm is a 9. The argument of the logarithm is the answer to the exponential equation. The answer to the logarithm is the power or the exponent. So this is a rearrangement of that. All right, so let me go back up to my notes for a second and write this down. In general, an exponential equation has a base, a power, and an answer. So 2 to the 5th power equals 32. 2, 4, 8, 16, 32. Okay, I had to do that on my fingers just to make sure I was right. A logarithm has a base, an argument, which happens to begin with the letter A, just like answer, and then the other side of the equal sign is the power. So log base 2 of 32 is 5. These right here are two equivalent ways of writing the same thing. And that is what you're practicing down here. Maybe what you want to do before you watch any more of the video, do number 25, do number 27, check yourself, and pause the video, do those, check yourself, and then come back to the video. I would suggest that. All right. Now we just the opposite here. We have logarithms. We need to change them into exponents. So an exponent has a base, a power, an equal sign, and an answer. The base is the little number by the letter g. The base of the logarithm and the base of the exponent are the same. The power here is the answer from the other side. That goes there. The argument of the logarithm is the answer to the exponent. So 3 to the second power equals 9. There it is. It's rearranged. Let's do this one. So the base is 16. The power is 2. And the answer is 256. This number goes here. This number goes here. That number goes there. This goes here. This goes here. That goes there. So again, you might want to pause the video and do 21 and 23 real quick. Just make sure you get it down. Okay, if you pause the video, you're back. So again, to summarize, a logarithm is just a different way of writing an exponential equation. It's just a different format, a different order, a different structure, however you want to say that. They're essentially the same concept. It's kind of like this. One last thing. If you say 2 plus 3 equals 5, a similar concept would be 2 equals 5 minus 3. They're different arrangements of the same kind of thing. You know that subtraction and addition are related. They're sort of opposites of each other in a way. Logarithms and exponentials are sort of related. They're kind of opposites of each other in a way. Okay, now let's get to actually solving equations using logarithms. Okay, so yesterday we would have had a 10 over here. These would have crossed out, and I would have had x equals whatever power was here, but that is not the situation. I have 10 to the x equals 40, and I need to somehow cancel out that 10. Now, the thing that cancels out a base is a logarithm. A log cancels a base. So I need to take a logarithm of this side of the equal sign. Now, all logarithms have a base. The base I need to use is base 10. Do you see how I left a space here? I did that on purpose because with equations, whatever you do on one side of an equal sign, you have to do the same on the other side of the equal sign. So I also have to take log base 10 over here. So you choose log base 10 because a base 10 is what you're trying to cancel out. It cancels, giving you x. The other side of the equal sign, log base 10 of 40, is something that you type into a calculator. So let me pull this up. Clear that out. So I need to type in log base 10 of 40. There's a function button on Desmos right there. If you hit miscellaneous, you'll see two log buttons. Down in the second to the bottom row, there's log and log A. I'll use log A right now to show you. So the cursor is blinking down there in the location of the base, so I can type a 10 there. And then the parentheses is where your 40 goes. And what I get is x equals 0.602, round to the nearest 10,000. So that's 4 decimal places, so 6021. That should be the answer. Let me check it real quick just to make sure I didn't screw anything up. I don't want to go on and on if I've done something wrong. There, 1.6021. That's right. I just realized I didn't check any of those last problems, but we'll live with that. They're okay. All right, so there it is. So to cancel out a base, you need to take a logarithm that matches that base, but what you do on one side, you also have to do on the other side, and when it comes to the other side, that's where you use a calculator. Uh-oh. 40. Doggone it. I'm such a maroon. Okay, maroon is a color. Moron is what I'm trying to say, but if I'm a moron, I don't know the right word, so I say maroon because I'm not smart. 1.6021. And that's a lot. That looks a lot like the answer that I checked, quote, air quote, checked myself with. Duh. 1.6021. Sorry about that mistake. Gosh, you're learning something new, potentially confusing, and I make a little mistake like that. Can't be good. Okay, I'm going to come back to number 2 in just a minute. but not yet. Let's do number 4. 16 to the b equals 36.05. So I just rewrote the problem with a space here. What is up with that space? Well, I need to cancel out that 16 in order to isolate my variable. What does it take to cancel out a base? It takes a logarithm. What type of logarithm? Every logarithm has a different base. Do I want to do a base 5 here? No, a 5 doesn't cancel a 16. I need to do base 16. I also have to do, therefore, log base 16 on the other side of the equal sign. The log base 16 and the base 16 cancel out. The other side, I'm going to do function log a, type in 16 down there, and 36.5. This keyboard is just not responsive. 36.5, 1.2975 if I'm rounding correctly. 1.2975, 1.2975. So there it is. So that is the heart of it. There's the fundamental process that we're going to be doing here. This is what's new today in pre-calculus. It's canceling out a base using a logarithm. Now, if you notice on this function menu, there are 2 log buttons. The one that I've been using, log base A, but there's also just plain old log. Oops. Let me do this again. Just plain old log. All right. So here's the deal. There are infinitely many types of logarithms. You can have log base 2, log base 3, log base 4, log base 5, right? Infinitely many of them. There's not infinitely many log buttons on a calculator. So this log base A allows you to choose any base you want. You want to do log base 5? Fine. You want to do log base 3? Great. Traditionally, historically, technology was not up to that spot. And calculators only had one log button, and it was the log button. This is called the common log. In fact, I'm going to write this down. LOG, no base written, is what we call the common log, logarithm, and it is equivalent to log base 10. Okay, log base 10. Our numbering system is called the base 10 numbering system. We have 10 digits, 0 through 9. Normally a person has 10 digits, 5 fingers on each hand. That's how our number system evolved, to be 10 digits, or base 10. So it's the common log because it's the one that happens the most common. It's the most common logarithm to do. What that means is, for number 2, I could have done it completely differently and still gotten the same answer. Let me leave the answer there and erase my steps. So I have 10 to the x equals 40, and I need to cancel out a base 10. If I simply do the common log of both sides, that should give me the answer. This cancels out the 10. I get x equals log 40. So let me do log 40. And there's the exact same answer. So if your base is 10, you can save about 10 seconds, 5 seconds, I don't know, by using the common log instead of writing in a little 10 here. You can use the common log button instead of the log A button. Do you want to? Does it make a big difference? At this point in technology, no, it doesn't make a big difference. They're both the same. But in terms of just having a well-rounded base of knowledge when it comes to math, you should know that a log with no base written is equal to log base 10. Will that work on this problem here? If I had 16 to the b equals 36.5, can I do the common log of both sides? Oh, my phone alarm's going off for no particular reason. Let me shut that off. Okay, sorry about that. Does this work? Well, no. A base 10 does not cancel out a base 16. If I type in to my calculator the common log of 36.5, it does not give me 1.2975. So you can't use the common log anytime you want. You're only going to use the common log when you're trying to cancel out a base 10. Okay, I beat that to death, hopefully. If you don't understand, it might not even be that important, but if you have issues, contact me. I'll try to explain it better if I need to. All right, number 6. Let's just start getting through these. 8 to the a minus 4 equals 2.2. To cancel out an 8, I need to take a logarithm whose base is also 8. I have to also take a log base 8 of this side. So I get a minus 4 equals function log a. The base is 8. The argument is 2.2, not 22, 2.2. I get 0.3792. But I'm not done because this has got more algebra. Now I need to add 4 to both sides. A equals 4.3792. That should be my answer to number 6. Let's check number 6, 4.3792. There it is. Let's do number 8. I do have a base 10. I do want to cancel the base 10, but I can't yet because this is being multiplied by 4. Now, can I multiply that and make it 40 to the x? No, you can't do that because there's no power here. They're not like, they don't go together like that. So you can't do that. You have to divide both sides by 4 to cancel out the 4 that's multiplied. So you get 10 to the x equals, what's 72 divided by 4? I'm a math teacher. I should know that in my head. 18. Now, this is a base 10, so if you want, you can just do the common log of both sides. Save just a second on your calculator. So common log of 18, 1.2553 should be my answer. Let's check number 8. 1.2553. There it is. Number 10. To solve this one, I'm going to need to start by adding 3 to both sides. 14 to the negative 6n equals 94. Notice I left a space here intentionally because I'm thinking ahead. My next step is going to be to take log base 14 of both sides. Why log base 14? Because I want to cancel out a base 14. You get negative 6n equals, here's where I need a calculator, function log a. The base is 14. The argument is 94. 1.7216. Now I need to divide both sides by negative 6 to isolate n. 1.721. Oh, doggone it. 1.7216 divided by negative 6. Negative 0.2869. Let's check number 10 and see if that's the right answer. Negative 2.2869. We are good. I'm just going to peek at number 12. Number 12, the answer is going to be 5. Let's come up here and see if the answer is 5. 0.5, sorry. All right, add 2 to both sides. 4 to the x plus 1 equals 8. Now, time out. We could solve this the way we did it yesterday. I can change this 4 to 2 squared. I can change that 8 to 2 cubed. 1-to-1 property gives me 2x plus 1 equals 3. Distribute 2x plus 2 equals 3. Subtract 2, 2x equals 1. Divide by 2. X equals 1/2 or equivalent to 0.5. But you can also use logarithms. So yesterday's worksheet can be completely solved using logarithms if you wanted to. Log base 4 of both sides, x plus 1 equals, grab a calculator, log a, the base is 4, the argument is 8, 1.5. Minus 1 on both sides, x equals 0.5. Same answer. I don't know. To me, it looks like the logarithm answer took fewer steps to do. So for what it's worth, you generally use logarithms when you can't use the 1-to-1 property. But you can use logarithms instead of the one-to-one property if you so choose. All right, let's do number 14. So I have 2 times 10. I can't multiply that and get 20. I have to divide the 2 to cancel it out. And of course, 0 divided by 2 is still 0. Now to cancel out a base 10, I need to take the log base 10 of both sides. You can use base 10 or you can use the common log. This cancels out. Negative 10x minus 7 equals. Now watch this. Function log 0. Undefined. It is impossible to take the logarithm of 0. It cannot be done. That's like saying, what power can you raise 5 to get 0 for an answer? How many 5s do you multiply together to get 0? It can't be done. There's no such thing. So number 14 is an example where there is no solution, or that symbol, like I used to use the null set. So number 14 had better be no solution, and it is. So if you get undefined on your calculator, no solution. Number 16. Okay, so this one can be confusing. Like a lot of people look at a problem like this and say, there's so many steps, I don't know where to begin. One thing you can do is sort of block out the exponential part. Just treat it like x. If this said 10x minus 1 equals 56, what order would you solve this? Well, you would start by adding 1 to both sides, and then you would divide by 10. Those would be your first 2 steps. So those are still your first 2 steps. Add 1 to both sides. 10 to 8p minus 1 equals 57. Divide both sides by 10. 2 to the 8p minus 1 equals 5.7. You know that, right? 57 divided by 10 is 5.7. Now, this is where I should have left a little space because we need to cancel out a base 2. I'm going to take log base 2 of both sides. Log base 2 cancels that base 2. I get 8p minus 1 equals, and let's use a calculator for this. So function log a, the base is 2, the argument is 5.7. 2.5109, but that 9 rounds up to a 10, which means I have to carry a 1. So there. Now I need to add 1 to both sides. 8p equals 3.511. Divide by 8. And 3.5, doggone it, 0.5511, laugh at me, roast me, I don't care, divided by 8, 0.4389, if I'm rounding correctly. Hopefully I am. Let's check number 16. Where is it? There it is, 0.4389. All right, couple more and we're done, because remember we already did that bottom section. Oh, but now we're going to do exact answer. So how do you get the exact answer? Well, one thing you do is you get rid of the calculator. This looks scary. How do we do this without a calculator? It's actually easier than what we've been doing, in my opinion. I don't know, maybe you'll find it more difficult. So here, I'm going to solve this. I'm going to start by adding 5 to both sides, right? Minus 5, you plus 5. 19 to the b plus 3 equals 68. Now to solve this, I need to cancel out the 19, so I need to use a logarithm. Logarithm cancels out a base. Log 19. That cancels out. I get b plus 3 equals. Now, this is normally where I type junk into the calculator. Well, don't. Just write down log base 19 is 68. Fine, just leave it like that. To solve this equation, I need to isolate b. I got a minus 3. So now I need a minus 3 on this side. I get log base 19 of 68 minus 3. There. That is the exact answer. Don't believe me? Let's check. Number 18, there it is. Log base 19 is 68 minus 3. Notice we didn't do 68 minus 3 and get 65 because this is technically grouped together. It's an order of operations thing. You can't subtract the 3 unless this has already been worked out. But since we're doing exact answers, we're not working it out, so you just leave the answer like that. So you're basically doing the steps without actually working out the answer. You're just proving that you know how to do the steps. If you needed to find the exact answer, you could then go and type this into a calculator and it would give you the exact answer. All right, let's look at number 20. Add 10 to both sides. 10 to the 5b equals 68. Move this over because this is the step where I take the log of both sides. Now, log base 10, you can use the common log. So you get 5b equals the common log of 68. Divide both sides by 5. b equals log of 68 over 5. Got ahead of myself, but that's a 68. Is that the answer to number 20? Yes, indeed it is. Okay, let's check these bottom ones that I didn't check before. So 22 should be 3 squared equals 9. 3 squared equals 9. 24, 16 to the second power equals 256. 16 to the second equals 256. So I better circle these answers. 24, log base 10 of 10,000 equals 3. Now I know that I could have written this as the common log of 1,000 equals 3. So let's check 26. Yeah, so they wrote it as a common log. 28, log base 9 of 9 equals 1. Log base 9 of 9 equals 1. Okay, that's the whole thing. If you have questions, contact me. You can also, search YouTube if you want to watch other teachers teach this. There's got to be a gazillion lessons out there. So if you don't follow or understand what I did, you might be able to find someone else who did it and go through that video. But not trying to pass the buck to someone else. Let me know if you have issues. Email me or type me comments. Otherwise, I will talk to you later.